Hello and welcome back everyone. In this final video on Green's theorem, we're going to talk about the flux version. So let's go ahead and look at the result. We still need all the same hypotheses that we needed for the other version of Green's theorem. So we need C to be a positively oriented, piecewise, smooth, simple closed curve in the xy plane, because we're only going to deal with two-dimensional versions of Green's theorem. And let D be the region bounded by C. We need P and Q, the components of our two-dimensional vector field, to have continuous partial derivatives in an open region that contains D. So think that we just look at D and make the region a little bit larger and get rid of the boundary. That would be an open region containing D. And then we have this result that this line integral of P dy minus Q dx, so it's changed, is equal to the partial derivative of P with respect to x plus the partial derivative of Q with respect to y inside the region. Okay, so why is this called Green's theorem for flux? Well, if you remember when we talked about flux integrals, we said that the flux of a vector field across the boundary of a simple closed curve was f dot n ds, and then we worked out a different expression for this line integral, and it was exactly p dy minus q dx. So this is a flux integral. It's the flux of a vector field across the boundary of a simple closed curve with outward pointing normal. And so Green's theorem says that this flux integral is equal to the divergence inside the region. So what this is saying is that the amount of material that's going across the boundary is equal to how the material inside the region is moving away or towards each other. So how it's diverging. And so this is another result for Green's theorem. It's relating how something's changing inside the region to an amount that's crossing the boundary. And we didn't talk about this for the other version of Green's theorem, but this is really a two-dimensional version of the fundamental theorem of calculus. If you think about what the fundamental theorem of calculus says, it says that if you take the values of a function at the endpoints of an interval and take the difference, so let's say f of b minus f of a, that's equal to the integral of the derivative of that function inside the interval, right? So the values of that function at the boundary points of an interval is equal to how that function is changing over the interval. Well, that's what's going on here. This is saying that the amount going over the boundary of my two-dimensional region is equal to how things are moving away or towards each other inside the region. This is kind of a derivative, right? And when you take divergence, you exactly get a derivative. This is also true for the circulation curl version of things. The kth component of curl, they refer to it in the book as the circulation density, right? So that's how the circulation is changing inside the region. So it's saying the other version of Green's theorem is saying that the circulation on the boundary of a region is equal to how the circulation is changing inside the region. So both of these Green's theorems, both for circulation curl and for flux divergence, are two-dimensional versions of the fundamental theorem of calculus. And if we have time this semester, we're going to get to three-dimensional extensions of both of these versions of Green's theorem. So for the circulation curl version of Green's theorem, if you move that to 3 dimensions, that's called Stokes' theorem. And for the three-dimensional version of the flux divergence version of Green's theorem, that's called the divergence theorem, or sometimes called Gauss's theorem. And we may not get to those this semester, but those are the other two really big important results in this course. So if we don't get a chance to actually cover them in detail, now at least have an idea of what they are. They're extensions of Green's theorem to 3 dimensions rather than just staying in the xy plane. Now, all of the extensions that we've talked about for the first version of Green's theorem work for this version as well. In other words, if you need to switch to polar coordinates, you can switch to polar coordinates. If you have a closed curve that has a negative orientation, you can still use this. You just have to change the sign of your double integral. So it's not equal to this double integral anymore. It's equal to the negative version of the double integral. And it's like the example we did in the last video. And we can deal with regions that have holes. We just need to make sure we have a positive orientation, meaning the boundary around the hole has to be traversed clockwise rather than counterclockwise. So all those apply to this version as well. So to close out this section, just want to do a simple example of using this version of Green's theorem. So there's just a quick example. So find the flux of this vector field 2xy plus x, xy minus x, across the square bounded by x equals 0, x equals 1, y equals 0, and y equals 1. So what does this look like? So here's the square. Looks like a rectangle, but you all know I can't draw by now. We're traversing it counterclockwise because when we introduced the idea of flux, we always said that we had to have a counterclockwise orientation to our closed curve anyway. If we wanted to compute the flux, we would need to set up 4 line integrals, 1 integral for each line segment here. And they'd be pretty easy line integrals to set up. It wouldn't be that much work. So we could compute this line integral of 2xy plus x dy minus xy minus y dx. But instead of doing that, let's compute the divergence inside this square. So the divergence of this vector field, I take the partial derivative of the first component with respect to x to get 2y plus 1. And I add the partial derivative of the second component with respect to y, which is x minus 1. And so the divergence of this vector field is 2y plus x. And now I need bounds of integration for this region, enclosed by my curve, but it's just a square. So my bounds are both going from 0 to 1. I'm going from 0 to 1 in the x direction. I'm going from 0 to 1 in the y direction. So this is a pretty easy integral. The double integral from 0 to 1 in both x and y of 2y plus x. Here I've set it up integrating with respect to x first, but since this is a square, we could just change the order of integration with no extra work. Even the bounds are the same. So it really doesn't matter here which variable I integrate with respect to first. So I integrate with respect to x first, and I get 2xy plus 1/2 x squared. And when I plug in 0, 1, that gives me the integral in y of 2y plus 1/2. And then I integrate with respect to y to get y squared plus 1/2 y. And my answer is 3/2. So it's just another example. The key thing here is that if you're asked to find flux across a boundary and you want to use Green's theorem, the important thing to remember is that the double integral is different. For the circulation curl version, right, it's the partial derivative of q with respect to x minus the partial derivative of p with respect to y. It's that third component of curl. But here for the flux version, it's the divergence. So it's the partial derivative of p with respect to x plus the partial derivative of q with respect to y. So the setup is different. So you really need to look when you're doing a problem, okay, are they asking for circulation on a boundary or are they asking for flux across the boundary? Because that's going to change how you set up your double integral if you try to use Green's theorem. It's also going to change how you set up your line integral if you decide to do the line integral, right? For circulation, the line integral was p dx plus q dy. But for the flux, it's p dy minus q dx. So another thing to keep in mind. All right, and that's it for section 16.4, talking about Green's theorem. And next we're going to start doing triple integrals.